Google's search index contains over 1 billion websites. Retrieval augmented generation promises to unlock this knowledge for LLMs. But here's what most engineers get wrong. 90% of RAG implementations fail to deliver relevant results. The secret is in the details. By the end of this video, you'll know how to design a RAG architecture that avoids common pitfalls and delivers accurate, context-aware responses. Remember this 90% failure rate. We'll see why this matters when we discuss evaluation metrics.
Let's define the scope of our RAG system. Functionally, we need to ingest documents from various sources, chunk them into smaller, manageable pieces, create vector embeddings representing the semantic meaning of each chunk, retrieve relevant chunks based on a user query, and finally generate a response using an LLM. Non-functional requirements include low latency retrieval, under 200 milliseconds, high accuracy, relevant results, the ability to handle 10,000 queries per second, and support for various document types. Clarifying questions. What document types do we support? PDF, TXT, HTML? What's the average document size and the distribution of sizes? Do we need real-time updates or batch processing? These questions help us understand the scale and complexity of the system.
Let's estimate our storage and bandwidth needs. Assume we ingest 1 million documents, each averaging 1 megabyte. That's 1 terabyte of raw data. If we use 768 dimensional embeddings with 4 bytes per dimension, each document requires approximately 3 megabytes of vector storage. Total vector storage, 1 million times 3 megabytes equals 3 terabytes. At 10,000 QPS and 1 kilobyte response size, we need 10 megabytes per second bandwidth. 10,000 QPS times 0.20 seconds latency equals 2,000 concurrent requests. This is where most people go wrong. They underestimate the storage requirements for embeddings and the impact on retrieval latency. Remember this 3 terabyte figure. It will influence our choice of vector database.
Now for the high-level design of our RAG system. We'll use a RAG architecture because it allows us to leverage external knowledge without fine-tuning the LLM, saving significant time and resources. First, document loading extracts text from various sources like PDFs and websites. Next, text splitting/chunking divides the text into manageable segments. Then, vector embeddings transform these chunks into numerical representations using models like OpenAI's Text Embedding Ada 002. These embeddings are stored in a vector database for efficient retrieval. At query time, the user's query is embedded and used to find the most relevant chunks. Finally, these chunks are passed to an LLM to generate a response. We'll expose an API endpoint, post/API/v1/query, query text, user ID, returns response text, metadata. The reason we chose this API design is to allow for asynchronous processing and user-specific rate limiting.
Let's dive into the core logic of our RAG pipeline. For chunking strategies, we'll use a hybrid approach, semantic chunking combined with fixed-size chunks. Semantic chunking uses sentence boundaries to create contextually relevant chunks, while fixed-size chunks ensure consistent input length for the LLM. We use cosine similarity for retrieval because it's robust to varying vector magnitudes, unlike Euclidean distance, which is sensitive to vector length. For re-ranking algorithms, we'll employ a cross-encoder model like BERT to refine the initial retrieval results. An interviewer might ask, why not just use BM25 for retrieval? The reason is that BM25 relies on keyword matching, while cosine similarity captures semantic similarity, leading to more relevant results. Query expansion can improve recall by reformulating the query with synonyms and related terms using techniques like WordNet. We ensure idempotency by assigning a unique ID to each query. Stop. Think about this. What happens if the query expansion introduces irrelevant terms? We need to carefully control the expansion process and use techniques like query rewriting to mitigate this issue.
Now let's discuss the data model for our vector database. We'll use Pinecone as our vector database because it offers high throughput and low latency similarity search, crucial for our 200 millisecond latency requirement. The schema includes document ID, UUID, chunk ID, integer, text, string, embedding, vector, metadata, JSON, created at, timestamp, job ID, UUID for data lineage, and budget consumed, float for privacy. Pause and think. What's missing from this schema? We need parent ID to track the original document for augmented samples. We choose Pinecone over Quadrant because Pinecone provides better scalability for our expected data volume, especially considering the 3 terabyte of vector embeddings we estimated earlier.
Let's scale the system to handle increasing load. We'll use caching to reduce latency. A Redis cache stores the most frequently accessed embeddings because it provides sub-millisecond access times, significantly improving retrieval speed. For replication, we'll use leader-follower replication for the vector database to ensure high availability. Sharding the vector database across multiple nodes improves throughput. We can use a CDN to cache the LLM responses, reducing the load on the LLM service. Remember those 1 billion websites? To handle that scale, we need to shard our vector database across multiple regions. The context window limitations of LLMs require careful chunk size optimization. We use A/B testing to determine the optimal chunk size for different document types. What happens if the cache goes down? We fall back to the vector database, but latency increases. That's why we use cache replication. Your interviewer will push back here. Why not use consistent hashing for sharding? The answer is that consistent hashing can lead to uneven data distribution when the data is not uniformly distributed. So we'll use range-based sharding based on document ID. Now let's consider reliability and fault tolerance. For fault tolerance, we'll use redundancy at every layer, multiple API servers behind a load balancer, replicated vector databases using Raft consensus, and redundant LLM instances. Monitoring is crucial. We'll track latency, throughput, error rates, and cache hit ratio using Prometheus and Grafana. Alerting systems notify us of any anomalies. Data source updates are handled via a scheduled job that reindexes the documents. If the embedding service fails, we retry the embedding generation process using an exponential backoff strategy. If the vector database becomes unavailable, we can temporarily switch to a backup database. This ensures that the system remains operational even in the face of failures. In summary, we designed a RAG architecture that balances accuracy, latency, and scalability. The key trade-offs include chunk size versus context retention and retrieval speed versus accuracy. Potential bottlenecks include the LLM inference time and the vector database query latency. Next steps include prompt engineering to optimize the LLM's response and evaluating the system using metrics like precision, recall, and F1 score. Remember that 90% RAG failure rate? Evaluating these metrics will help you avoid that pitfall and build a successful RAG application.
If you found this helpful, please like, share, and subscribe for more technical deep dives like this.